all, I don't want to start talking about vipers. I'm going to start talking about coral reefs. So coral reefs are widely known by their exceptional diversity that is mostly endangered all around the world. And specifically, the coral reef fishes represent a scenario that is widely debated in the literature. So this scenario illustrates a lineage that invades a new habitat, and this invasion will lead to an explosion of both species and morphological diversification. And in fact, many studies suggest that coral reef fishes are more species-rich and phenotypically diverse compared to their sister lineages of non-coral reef fishes. So coral reef fishes represent an habitat shift that will increase the ecological opportunities faced by the lineage, that consequently will increase the morphological and species diversification. And in fact, these three situations, an increase in ecological opportunity, increase in morphology diversification, and species diversification, comprise the conditions that where an adaptive radiation, the famous adaptive radiations, take place. So here I include this figure that illustrates different evolutionary radiations, not only adaptive radiation. And here we have on the axis the species richness, phenotypic disparity, and the frequency where clades occur given the combination of species richness and phenotypic diversity. And as you can see, the classic adaptive radiation here represented by the African cichlids are far from being the rule in nature. So what I want to talk about here is not about a situation where an adaptive radiation takes place. I want to talk here about a situation that might be the opposite case. So imagine a lineage that also invades a new habitat, but the interaction with the lineage with the environment will not spur rate with species diversification. And in fact, will prevent the lineage to diversify. So this situation is what we think that might happen when an arboreal lineage of snakes invade a lineage of snakes invade the arboreal environments. But why do we think that this happens with snakes and the arboreal habitats? So arboreal snakes are known by having many behavior, physiological, and morphological adaptations. The literature suggests that they show different morphological syndromes, which suggests that they have phenotypes that are very similar to each other. In contrast, terrestrial snakes are known by having a much more generalized morphology. So we expect that arboreal habitats and terrestrial habitats will represent different adaptive scenarios. So terrestrial habitats will comprise multiple adaptive peaks that reflect the great variance in the morphology that we see among the terrestrial snakes, where the arboreal habitat will comprise only one main peak, which must be reached by all arboreal snakes in order to be able to live in the arboreal habitat. So given this scenario, we expect that evolutionary forces that maintain phenotypes very close to each other, like stepwise selection, will increase in the arboreal habitat. In contrast, the evolutionary force that generates phenotypic diversity, like divergent selection, will decrease in the arboreal environment. And this lack of phenotypic variation among the arboreal lineages would have an impact on the speciation rates, and we expect that speciation rates would be smaller among the arboreal lineages. So we elaborated two hypotheses to explore the scenario. So we expect that arboreal snakes will have a more constrained morphology, and that speciation rates will be higher among terrestrial lineages. And to explore these two hypotheses, we choose to use the lineage of vipers for several reasons besides their ability. And arboreality evolved multiple times among the group, as you can see through the green branches. We also have arboreal vipers are distributed all around the world in different continents and are not restricted to a certain region in the world. And we also have a molecular phylogeny comprised summarizing 80% of all viper species, that is 264 species. We also gather morphological data for different morphological variables, and we also have information for all the species in the phylogeny. So we categorize vipers as being arboreal or terrestrial, and we split the terrestrial category into 3 subcategories. There is snakes restricted to open habitat, restricted to forest, and those occurring in both habitats. With the added information, we reconstructed the evolutionary history of habitat and used these reconstructions to fit different models of trait evolution to explore how the body size evolved differently between habitats. So, 2 parameters will basically describe the evolutionary trajectory of traits, and are very important to understand the results. So, the first parameter is the phenotypic variation, phenotypic rate, and it's something like the diversifying force of drift, although it's not the same as genetic drift. So here is a simulation of a trait evolving with a given value of sigma, and if you increase the value, you have a higher variance of final phenotypic values. The other parameter is the strength of selection, or alpha, and if you change out the value of alpha, like here, once the trait starts evolving from a different value related to the optimum, that is here, which is the case, it rapidly achieves the optimal value. What this does not happen in this situation here. It takes more time to achieve the optimal value. So we expect that these 2 parameters will give us indications of the different evolutionary trajectory the body size will have in the different habitats. To explore our second hypothesis, we use MUSI method implemented in the Bayesian framework, and we expect that MUSI will suggest for us that arboreal snakes will be related to smaller speciation rates. So these are the raw data for body size, and you can see that the body size for arboreal snakes are concentrated in a short interval of values compared to the other habitats. But this is only the raw data. So the OE method that we use suggests that the best model for body size evolution is that body size is evolving under an unevent process, which involves selection. But instead of evolving towards only one main adaptive optima, body size is evolving toward different phenotypic optima related to each habitat. Additionally, both the parameters that I mentioned before differs across the habitats, so this indicates the body size that have different evolutionary trajectories in each habitat. So here are the body size optima estimated by OE, and we can see that body size optima are more confidently estimated for arboreal vipers. Snakes in restricted open habitats tend to evolve towards smaller body sizes, where the ones that occur in both habitats tend to evolve toward larger body sizes. However, the parameter of strength of selection seems to be much estimated with stronger values for among arboreal snakes. And so arboreal snakes are evolving under stronger strength of selection compared to the other habitats. And the other parameter, the phenotypic rate, seems to be smaller among arboreal snakes. So they are evolving under smaller phenotypic rates compared to the other 3 habitats. Different from what we expected. Wow. MUSI method didn't suggest any different speciation rates between habitats, so they all seem to have very similar speciation rates in all the habitats. So, although body size seems to be very constrained among arboreal vipers, this lack of phenotypic variation seems to be decoupled from speciation rates, which remain the same between habitats. So it is feasible to suggest that the mechanisms that generate species in the arboreal habitats generate species diversity without generating phenotypic diversity. And this mechanism seems to play a significant role among the arboreal lineages because they prevent the speciation rates to decline once the lineage invade the arboreal environment. So I would like to thank my lab, FAPESP, for financial support, and all the researchers that gave me information about vipers ecology. Thank you very much.